All right, so today we are very happy to have Amalendu Krishna from TIFR, who will tell us something about Chow groups and Euler class groups of affine varieties. Yeah, you can go ahead.
Yeah, so thanks, Eldon. So I would like to thank the organizer of this seminar for this opportunity to give this talk. So this talk is about some results on Chow groups and Euler class group of affine varieties over algebraically closed fields. So everybody can hear me, right? Okay.
Yeah, you're good.
So let's go ahead.
Yeah, we can all hear you.
Yeah. So basically, I will present two results on the Chow groups of zero cycles on affine varieties over algebraically closed field and give some consequences. So let me begin with some motivations. So the starting point is the famous torsion theorem of Roitman. So the description of the torsion group of an invariant of algebraic variety is, as all of us know, that it's an important problem in algebraic geometry to find the torsion group. So we fix a base field K, which is going to be algebraically closed. And the invariant we want to study is the Chow group of zero cycles. So let Chow group like CH0X sub 0 denote the kernel of the degree map if X is projective over K. So if X is smooth and projective, then we know that it has the associated Albanese variety, which we write as Alx, which is a abelian variety, which has the universal property that it receives a map from X, and any morphism from X to any other Albanese variety actually uniquely factors to this up to some translation. So, and if this coincides with the Jacobian variety, if X is a smooth projective curve. So any choice of a base point, the close point P gives rise to a morphism of schemes, as I said, X to Lx. This we call it Albanese morphism, so that it takes that point to the identity element of the Albanese variety. The Albanese map allows one to define a group form morphism from Chow group of zero cycles to the k-rational points of Albanese variety, which has the obvious definition. Just take the sum over the images of the closed points. And this does not depend, once we take the degree zero part, you can see that it does not depend on the choice of the base point P. Now, a remarkable theorem of Roitman says that this alpha X induces an isomorphism between the prime to P torsion subgroups if characteristic of K, exponential characteristic is P. Later, Mills showed that alpha X actually is an isomorphism between the full torsion subgroups, namely, you take the torsion subgroups of the Chow group and the torsion subgroup of the k-rational points of the Albanese variety. Actually, this is an isomorphism. And remember that the torsion subgroup of degree zero part is same as the torsion subgroup of the whole Chow group, so I don't need to write degree zero anymore. So note that one knows if everybody knows that if you have an abelian variety, you have a very clear description of its torsion subgroup. So in particular, you get a very good description of a complete description actually of the torsion subgroup of the Chow group of zero cycles on smooth projective variety. So that's the beautiful point about this theorem of Roitman. So the above results motivated the following question, which we call the affine Roitman torsion problem. It says that let X be a smooth affine variety over K of dimension at least 2. Then the question is the Chow group of degree zero, Chow group of zero cycles torsion free? So remember because the thing is that for affine variety, they have no Albanese, so you should expect that it has no torsion basically. And you'll see why you should expect this. And the dimension D at least 2 is very important because you can clearly see that if dimension is 1, then this is not going to be true. So, and the following result is due to Murthy, and what the result says that the affine Roitman torsion problem has a positive solution. Remember that this is for a smooth affine variety. So in particular, if you take a smooth affine variety of algebraically closed field of dimension at least 2, then the Chow group of degree 0, Chow group of 0 cycles has no torsion actually. And it has a lot of very non-trivial consequences, as Murthy himself proved. So let me try to show you that how you can deduce this affine torsion theorem from the Roitman torsion theorem for smooth projectives, let's say for surface. Just because we are going to use this later, so let me just give you some idea of how to prove this. Okay, so here it goes. So let's start with a smooth affine surface, and then you can always put it inside a smooth projective surface such that the complement is a simple normal crossing divisor. Because you in dimension 2 you have resolution of singularities, so you can do that in any characteristic. So then a theorem of Goodman's implies that y actually is an ample divisor on x because x is a surface. So in particular, because x is at least dimension 2 is ample divisor, it must be connected. That's the first observation. And then you have this localization sequence that because y is connected, so you have, if you take the degree 0 part on the left and the middle, you have an exact sequence like this. It's just the usual Fulton localization sequence. So now let F denote the image of this iota lower star. And then remember that it's not hard to see that the Chow group of degree 0 cycle is always a divisible group because you can always reduce to the case of curves, and curves, it is a Jacobian variety, so which is clearly divisible. So F is a divisible, in particular it's an injective as a module, so actually you get a like exact sequence which is actually a split because this is injective as an abelian group. Yeah, so yeah, you just need only this sort of exact sequence. So now so again, because y supports an ample divisor, it's not hard to see that the image of y under the Albanese map must generate the Albanese variety. This is a observation in algebraic geometry because, you know, like if it does not, then you go modulo the Albanese of y, and then you get this map, and then it takes, you can choose a point, the p in y itself, then it takes y to 0 in the quotient al x mod al y. But then you have a morphism of variety in which the whole y is in the fiber, but any fiber of a map cannot be ample actually. So that is a contradiction. So it must generate the full Albanese. So it follows that this if you take the sum of the Albanese of all components of y, then this is surjective. So in particular,
I have a question. I have a quick question. So is this, I mean, it's some kind of Lefschetz hyperplane theorem, right? This is what you're using?
No, there is no Lefschetz here. And I just proved that y must be ample. And it's I just showed that if you have an ample divisor, then its image always generates the Albanese.
That doesn't use some kind of Lefschetz hyperplane. That's just
no, it doesn't. It just uses ampleness because, you know, like ample divisor must intersect any other subvariety positively. That's
okay.
one of the Nakai criterion in algebraic geometry, so to speak. So if it lies in the fiber, then if you take some other fiber, it's not going to hit. So it destroys the ampleness then. So just ampleness forces that it should generate the Albanese variety.
Thank you.
So, sorry, but could you clarify that a little bit more? Because I mean, I guess it wouldn't be true for a curve, right?
Sorry.
So I mean, I guess it wouldn't be true for. I mean, is there some additional hypothesis needed? Like, I was just wondering what the general statement here is.
Actually, yeah, and general statement is that if you take like any such like nice complete intersection curve also, then it will generate the Albanese variety, because you can reduce by hyperplane the dimension, and then you can see that even the generic curves will generate the Albanese variety. But here I don't need it. I just need to know that this my y generates the Albanese, image of y generates the Albanese variety. That's crucial. So in particular, if you take the Albanese of all the components, then it surjects. But then we know that it's a simple fact that if you have a surjective map of, in fact, commutative algebraic groups, here is abelian variety, then it must surject also on the torsion groups. It's not difficult to see. But then basically what happens then? Then, like the torsion subgroup of Y surjects onto the torsion of X. But then the Roitman torsion theorem tells you that the torsion of Chow group is same as torsion of Albanese. That means that all torsion of X actually comes from the torsion subgroup of Y, which means from this exact sequence that this guy must be 0. The torsion of X must be 0. So this is the proof of affine Roitman torsion theorem. But this proof does not generalize in higher dimension, because you cannot embed inside a smooth projective variety in characteristic P at least. And then you don't have Goodman's theorem, which says that if the complement will be ample or something. So it doesn't prove like this. So Murthy has a different proof, but again using very strongly the smoothness condition. So yeah, so this is how the smooth Roitman, affine Roitman torsion problem is. Now my main interest is Roitman torsion problem for singular affine varieties. So what is this? So, so now let X be a singular affine reduced scheme of dimension at least 2 uppercase. Any affine reduced scheme, no condition. So then the correct cohomological Chow group of 0 cycle in this case was defined by Levin and Weiwel, and its definition is basically same as the Fulton's definition. There are 2 differences, namely you don't take the closed points which lie on the singular locus. That's the meaning of the numerator here. And in denominator, you take those curves in the rational equivalence, which along the singular locus, they are sort of like local complete intersection, not arbitrary curve. So you see, along the singular locus, you put some condition. And this condition has basically the idea behind this condition is that then the inclusion of C inside X is a regular immersion. So it's a finite 2 dimension. So you can push forward cycles, or you can take push forward on K theory. So you don't need this in a smooth case because the map is automatically a finite 2 dimension. But here you have to put this condition. So once you do that, then basically the group you get is some new group, which is slightly modified version. We'll call it the Levin-Weiwel Chow group. So it's clear that if X is smooth, this is the original classical Chow group of 0 cycle by the definition. We can see this. So now the question is this, that is Chow group of Levin-Weiwel Chow group of X torsion 3? This is called the affine general Roitman torsion problem. So this is a question. And the first main result today is the following, that theorem A, that actually answer is yes, that the affine Roitman torsion problem has a positive solution for any reduced affine scheme of dimension at least 2.
So there's a question in the chat, Amalendu. The question is, do we have higher Chow LW underscore I? Do we have,
yes, we do have, but we do have, but situation is not very clear at this moment. But there are definitions, yes. Yeah, there are definitions, yes. But right now we will do only 0 cycles.
Thank you.
Yeah. So So I will give a sketch of this result towards the end of the talk. So only thing I would like to say here is that this result cannot be deduced from a smooth case. Moreover, unlike the smooth case, we cannot use projective Roitman torsion theorem even in dimension 2, because no such theorem exists for a singular projective variety in positive characteristic. You don't have Roitman torsion theorem. In the characteristic 0, you do have, but not in positive characteristics. So you can't do that. You can't use that. So in fact, the dimension 2 case of this theorem A is the most subtle part of the proof. Okay, so now let's go to the second theorem I want to state today. So let X be a affine scheme as above. Then you have a cycle class map, again from the Levin-Weibull Chow group to K0. This is the Grothendieck group of vector bundles on X. So what is this map? You just take any close point to its class in K naught. Remember, there again you use that X is a regular close point. Otherwise, you cannot have a class in K naught. So this makes sense. So now you let F0, K0, X be the image of this cycle class map. And it's not hard to show that this image is basically the bottom piece of the gamma filtration of K naught. Okay, so here is the second result of this talk, namely that the kernel of the cycle class map is annihilated by d minus 1 factorial. Remember that this result is completely classical. If X is smooth, then it was already proven by Grothendieck. But for singular variety, it was not known that kernel is annihilated by this or not. But the answer is yes. Okay, so these two are my main results, and now I will. It's not clear right at this moment that why they are important, but let's see the applications. So first application is Murthy's conjecture. So let's see what it is. So Murthy conjecture that if you have any affine, reduce affine scheme over algebraically closed field of dimension at least 2, then this F0, K0, X is a torsion-free group. This was conjectured by Murthy in his very famous paper in 1980s or something. And one of the application of theorems A and B is that the Murthy conjecture is actually true, that this group is a torsion-free group. So I should tell you that Murthy papers actually proves where he made this conjecture. Actually, he asks a question, but Murthy always asks a question. He never writes conjecture. So he proves many results in his paper, but most of the result is under this assumption that this conjecture holds. So what is the proof? Assuming theorems A and B of Murthy's conjecture. So well, it follows from theorem A and B that the map from here to here is an isomorphism, right? Because theorem B says the kernel, this map is clearly surjective, of course, by definition. And theorem B says the kernel is torsion, but theorem A says that this the source of this map has no torsion. So that means that this map must be an isomorphism, but the source is no torsion, so the target also cannot have torsion. So that's the proof.
Are you assuming something like equidimensional X, dimension greater than or equal to 2?
Equidimension?
X could have a one-dimensional component.
Actually, yeah. I mean, the variety is allowed to have components of several dimensions. In that case, any component which does not have top dimension will be the part of my singular locus. So by definition, my singular locus is the actual singular locus of X union all the components which have dimension smaller than the maximal dimension.
Okay, thanks.
Yeah. So that's the proof of Murthy's conjecture. So let's go ahead. Now let's go to the second application. So second application is about splitting vector bundles. So what is this? So let X in general be a Noetherian affine scheme of full dimension D. Then a classical result of Sayre says that every vector bundle on X of rank more than D has a nowhere vanishing section. Equivalently, it splits off a trivial line bundle. However, the problem of finding a nowhere vanishing section becomes highly non-trivial for a vector bundle whose rank is bounded by D. This is so-called the unstable range of vector bundles. We shall study this problem for vector bundles of rank D. Less than D, the picture is still very, very unclear, even for a smooth varieties. So we shall assume, as before, that X is a reduced affine scheme of dimension D over an algebraically closed field. Mumford then showed that there exist vector bundles over X of rank D which do not admit any nowhere vanishing section, even if X is smooth. So the Sayre theorem does not hold in dimension D. That's what Mumford proved. So then the question arises as to what are the necessary and sufficient conditions on a vector bundle V for it to admit a nowhere vanishing section. So Murthy proved a remarkable theorem. What is his theorem? Recall that if V is a vector bundle of rank D on a smooth affine variety, then it has its top Chern class, which I denote by CDV, which lies in the Chow group of 0 cycles, right? Because this is same as the Chow group of 4-dimension D cycles. Now here is the theorem of Murthy. Murthy says that if X is a smooth, then V admits a nowhere vanishing section if and only if its top Chern class vanishes. So that's the very beautiful theorem of Murthy, that you just need to check what happens to its top Chern class. Okay, so now it was shown by Levine that for any reduced affine scheme of dimension D over K and any vector bundle V on X, there is a canonical top Chern class CDV in the Levine-Weibel Chow group. Now the second application of theorems A and B is the phonic generalization to any reduced affine scheme, need not be a smooth. So let X be a reduced affine scheme of dimension D over an algebraically closed field, and let V be a vector bundle of rank D on X. Then V admits a nowhere vanishing section if and only if the top Chern class vanishes. So it basically gives you a theorem for any sort of arbitrary affine scheme. So this is another application. And what's the proof? Okay, let's see a proof of this. Well, it's easy to see that if V has a nowhere vanishing section, the top Chern class vanishes. It's not hard to see. One very quick way to see is that, remember, if you have a similar variety and it's a fine variety, so you can always invite inside a smooth variety, right? And then, and such that the vector bundle comes from that smooth variety. It's a fact that every vector bundle on a quasi-projective variety comes from a smooth variety by some embedding. You can take some, for example, the Grassmannian of the vector bundle of that rank. So, and then for a smooth variety, this is clearly true. So then if you pull back to be X, then you will have the top Chern CDV will be 0. So now we suppose the main problem is this. They assume that the top Chern class is 0. How do you show that it has a nowhere vanishing section? Now we can define K-theoretic Chern class of V by CD tilde as this alternating sum of the exterior powers of the classes of the dual of V in K naught of X. This is called the K-theoretic Chern class. Now Murthy showed that actually this class always lies in the classes of 0 cycles, namely F0, K0 of X. Furthermore, one can show using the construction of the CDV that image of this K-theoretic Chern class under this map F0, K0, X to this Chow group, the Chern class map, is actually the top Chern class. Moreover, the composition from this composition is actually multiplication by D minus 1 factorial. And once you know that, then it's very easy to see that if, if the top Chern class vanishes, that this composition is 0, but this composition is D minus 1 factorial. But then we know that this group is torsion free. That's a Murthy's theorem, which Murthy conjecture we just proved. So that means that this K theoretic churn class must vanish. And then Murthy already proved, assuming his conjecture again, that if the K theoretic churn class vanishes, then we must admit a nowhere vanishing section, assuming his conjecture. But now I know that we know his conjecture is true. So this proves this splitting problem. Yeah. So now let's go to application 3, which is the connection between Euler class group and Chow groups. So when X is a affine scheme of dimension at least 2 over a non-algebraically closed field. Remember, so far we were using algebraically closed field. But if it is field is not algebraically closed, then one knows that the vanishing of top Chern class is not a sufficient condition for a vector bundle of rank D to admit a nowhere vanishing section. So for Murthy's theorem, it was very crucial that the field is algebraically closed. And there is a well-known example already in dimension 2 of a smooth surface actually. And this dimension is basically well known. Namely, you take A equal to the coordinate ring of real sphere of dimension rank 2. Just take S2. And then you define a map from A3 to A, namely f of EI equal to Xi, where E1, E2, E3 are the standard basis of A3, and take P to be the kernel of F. And then this relation tells you that this map is surjective. In particular, P is projective, and you have this P direction A is A3, namely P is stably free. Now it's easy to see using fundamental exact sequential Euler differential that the vector bundle associated with P is nothing but the tangent bundle of X. You can very easily see. Now, since P is stably trivial, and remember the Chern class factors to the K0 class, Guthandi group already. But a stably trivial vector bundle has trivial class in K0. So its C2P vanishes. But it's a well-known topological fact that the tangent bundle of S2 does not admit a nowhere vanishing section. Hence, P cannot admit a nowhere vanishing, because if you have an algebraic nowhere vanishing section, even topologically it's a nowhere vanishing sections, which doesn't exist actually. So actually, I don't know any algebraic proof of this fact that it does not admit a nowhere vanishing section. It follows from some topological fact. So I still don't know if is there an algebraic proof of this. Okay, so we see that non-algebraically closed field situation becomes much complicated. Okay, so here is Nori's proposal. So this shows that if we need to modify the Chow group and Chern classes. Nori proposed such an invariant, which he called Euler class group E0x. Actually, I should not write E0x, it should be just EX. He showed that every vector bundle V of top rank with trivial determinant admits an Euler class EP in EX, and asked the question if its vanishing implies that V admits a nowhere vanishing section. So this is Murthy's question. With the same purpose in mind, Barge and Morel defined the notion of Chow-Witt groups of a smooth varieties, not necessarily affine and not necessarily in fact in top degree, and constructed Euler classes of vector bundle in the Chow-Witt group. And they also asked the question similar to Nori, namely if the vanishing of Euler class implies that the bundle has nowhere vanishing section. Let me recall the definition of Euler class group for any Noetherian ring of dimension at least 2 due to Bhattacharya and R. Sridharan. This is not the definition of Chow-Witt group by Barge-Morel. This is just Euler class group. So what's the definition? So let K be any field and A reduced affine algebra of dimension at least 2. Take f of A to be the free abelian group on the set of pairs J, omega J, where J is an ideal of height D and J is M primary for some maximal ideal M of A. And third condition is you have some fixed orientation, namely take A mod G to the power D surjects onto J mod J square as an A mod J model. So let J, omega J be the class of this in F of A. Now given an ideal I of height D, let I be, you can write I as intersection of, write it its irredundant primary decomposition, where each Gi is Mi primary for some maximal ideal Mi of A. So if omega I a mod I to the power d to I mod I square is a surjection, then Chinese remainder theorem tells you that it uniquely defines surjection for every a mod Gi to the d to Gi mod Gi square. In particular, these are all in f of a, so you can write I comma omega I equal to sum of these classes. Note that this is well defined because irredundant primary decomposition is unique, at least in our case. Let K be the subgroup of F of A generated by elements of the type I comma omega I, where I is an ideal of height D with an A linear surjection such that this diagram communes. So basically what it is saying that you have chosen an orientation for I mod I square, but this orientation should lift to a generation of I itself. This particular thing should lift, not some general. It's not that saying that I is generated by D element, that's not enough. This diagram should come here. So then you write quotient E of A as F of A modulo K of A. It's called Euler class group of A. So this orientation is going to play a very important role. So you can imagine the Euler classes of in like for topological, real topological bundles. So now Euler class of a vector bundle, let's now assume that P is a projective A module of rank D together with an isomorphism chi from R to the top determinant of P. I am assuming the determinant of P is trivial. You don't need to do that, but let's assume that. You have to modify the Euler class group. We have to associate one line bundle associated to it, but let's just assume this. So this is a fact in this case that there is an ideal J of height D and a surjection P to J. This is some kind of sort of moving lemma. You can always do that. So let gamma bar from R mod J to the D to P mod JP be an isomorphism such that if we take this top exterior, then it becomes this the chi bar, which is chi mod J. We now have these maps from R mod J to D to P mod JP to J mod J square. And the Euler class of P is actually just this class J comma omega J. And one shows that this is well defined under some mild conditions. It is in particular well defined if A is a smooth affine algebra over infinite perfect field. But if A is not a smooth in characteristic P, it's not known that this is well defined. In particular, you don't have, it's not clear whether you have Euler class in that case for non-smooth algebra in positive characteristics. So then the question is E of A equal to Chow group of A when K is equal to K bar? So what's the relation between Euler class group and Chow group? So it's not hard to see that if P splits, then if and only if the Euler class group is 0. That's not hard to see. Thus, E of A is an invariant of A which can be used to detect existence of nowhere vanishing section of top rank vector bundle on X without assuming any condition on the base field. So let us now assume that A is a reduced affine algebra of dimension D over an algebraically closed field. We have seen earlier that in this case, the vanishing of top Chern class in the Levin-Weibull-Chow group also detects the existence of nowhere vanishing section. So this brings us to the following important question. Is it true that the Euler class group is isomorphic to the Chow group if K is algebraically closed? Because both are detecting nowhere vanishing section. So does it say that actually both groups are actually same? That's the question. And this question was answered affirmatively by Bhattacharya and R. Sridharan when A is smooth over K. Now the third application of theorems A and B removes this smoothness assumption. So the theorem is that the above question has a positive answer. In particular, if K is algebraically closed, then this Euler class group does not do anything new. It's basically just the Chow group. So the proof of this result goes into many steps actually. So note that a priori we do not even have a homomorphism in either direction, right? It cannot, if you think about it, there is no obvious map from Euler class group to Chow group and vice versa. In order to solve this problem, we need to recall the notion of weak Euler class group of A. So what is weak Euler class group? So let J be the free abelian group on set of ideals. So basically it's exactly same as the definition of Euler class group. Only definition is, the difference is you do not fix the orientation. So it's not like generators are not like J comma omega J, it's just J. But this has a condition that J mod J square is generated by D elements, but you don't put this omega J as the part of the definition. That's the difference. This then is called a weak Euler class. And the rest is all same basically. So then it's clear that if you define, and let's call this a E0 of A, then by it's clearly forgetting the orientation gives you a surjection from E of A to E0 of A. The Euler class group to weak Euler class group. Now, you see that even from the weak Euler class group, there is no obvious map to Chow group actually. Why? Because you see that if you take an ideal J, which is M primary, but this support of this ideal may be the singular point of X. So remember that the J is allowed to have singular support, but the Chow group does not allow its generator to have singular support. So there is no map a priori from Euler class group, weak Euler class group to Chow group. So you have to do some further modification. So what we do is that with the trick we play, we define a new version of weak Euler class group. So let's GS of A denote the free abelian group on set of a smooth maximal ideals. So we don't take some arbitrary like M primary ideal. We just take a smooth maximal ideal, just like in a Levin-Weibull Chow group. We shall say that an ideal I of height D is regular if it is of the form intersection of Mi, finite intersection of course, where each Mi is a smooth maximal ideal. And Mi is not equal to Mj for I not equal to J. Given a regular ideal A, let's set I equal to this sum as a class, and let Hs of A denote the subgroup generated by I, such that I is a complete intersection in A. So you just kill the classes of complete intersection, and you take the quotient. Let's call it the ES of A. This is some new definition I make, and you will see how it helps. Well, you can clearly see now that since the generator of ES are a smooth maximal ideals, there is clearly a map from ES of A to Chow group. So you have this diagram now. So you have a map from E of A to E0 of A. It's just a forgetful map. You clearly have a map from ES of A to E0 of A because generators here are smooth maximal ideals. So they are themselves M primary. So you have this map. And you clearly have a map from ES of A to Levin-Weibull Chow group. So there is a zigzag like this. And actually, it's not hard to see that the complete intersection ideal, if their class in Chow group vanishes, you can work by induction, and then for curve, it is very easy to see. So, yeah, and remember, our goal is to show that there is an isomorphism from Euler class group to Chow group. So we have this diagram here. And what we prove is the following. So here is the theorem. We prove that all arrows in this diagram are isomorphism. So all alpha, beta, and gamma I claim are isomorphism. Hence, there is an isomorphism from Euler class group to Chow group. So this is, it goes in a very indirect way. So this is the proof. That you have to prove that all three are isomorphisms. So actually this isomorphism between Euler class group and weak Euler class group is essentially classical. I should only tell you that there is one very non-trivial ingredient which is used is the cancellation theorem of Susslin. So Susslin's theorem says that if K is algebraically closed and if you have an affine algebra over K, then any stably free vector bundle of top rank is actually 3. That is used here very crucially, and that uses algebraically closed field in a very essential way. That is why it happens that the weak Euler class group and Euler class group are same over algebraically closed field. That's essentially the ingredient of alpha. Beta is not very hard. And the gamma is also uses gamma. Actually, remember, so far in alpha and beta, I have not used my theorem A and B. But to prove that gamma is isomorphism, I use theorem A and B. So let me just give you a sketch of why. I mean, beta is. Let me just give you a sketch of why. Maybe I should. I mean, basically the point is that it uses theorem A that this group F0 K0 A is torsion free. So the point is that you take a class in ES of A. Suppose a class dies in Chow group, then it dies in K0. But then if you have a local complete section regular ideal, which class dies in K0, namely A mod A, and if F naught K naught is torsion free, then Murthy already proved that then J must be a complete intersection. But you see, again, it uses Murthy's conjecture. So, but now we know this, so it follows that J must be 0 in ES of A. So it proves that gamma is injective, gamma is clearly surjective, so it's an isomorphism. So this is where I use this theorem A here, theorem A and B both. Yeah, so that basically another application. So it says that over algebraically closed field, Euler class group is basically Levin-Weibel Chow. Okay, so now let me give you a sketch of proof of theorem A. It's a very, very bad sketch because it's very difficult to give you a complete proof. So, so remember the theorem A asserts that this Chow group of X is torsion free if X is reduced affine scheme over algebraically closed field of dimension F is 2. So the proof of this is divided into two steps. We first prove the case of surfaces. Then we use a Bertini argument to reduce the higher dimensional case to that of a surface. So basically that's the idea, like you first prove for surface and then you use some Bertini argument to reduce to the case of surface. So let me show it for the baby case of a affine surface. So now let X be a reduced affine surface over K and let pi from X bar to X be the normalization map. Let W in X be a conductor scheme and W bar be its inverse image, the scheme theoretic inverse image. Then the first claim is that there is an exact sequence like this. So where this is the Jarsky cohomology of K2C and this is SK1 and there is an exact sequence like this. Now, remember X bar is normal surface. So it's uniquely divisible because it's normal. And the proof of this is very similar to the smooth case. Remember, in the beginning of the talk, I gave you a proof of if X bar was smooth, then why it is uniquely divisible. I should tell you that it is actually not only torsion free, but divisible also. So in particular, my claim is that the Chow group is actually a Q vector space. And if X is normal surface, then the proof is exactly same as in the smooth case because we know Roitman theorem for normal projective surface. This is a theorem of myself and Srinivas. So we know that this is uniquely divisible. Now let's see this. Well,
sorry, I have a question.
Yes.
So it's necessary. So you do use a version of the Roitman torsion theorem for normal projective surfaces for this X bar.
Yes, I do use per surface. Yes.
So that's a very non-trivial input, I guess. That's
it's a very non-trivial input here. Yes.
So somehow, even though the torsion theorem is not true for a higher dimensional normal variety, but it is true for a normal surface. That's what you're saying. The projective version of the torsion theorem.
Yes. Right. The projective, projective version is true for normal surface, and I use that very crucially. Yes,
but right. It's not the torsion theorem. The Roitman torsion theorem is not. Is it not true for higher dimensional norm? Higher dimensional.
It's true for high. It's true for normal varieties, normal projective varieties.
Okay.
but it's not known for arbitrary singular varieties.
Thank you. Yes. Okay. So for normal varieties, you can expect the
Yes.
the projective Roitman torsion theorem. Okay.
Yes, yes, yes. It's known. It's known. It's known. That's that's the theorem. Yeah, which I was just quoting. I need only for surface, but it is true for all in all dimensions.
Right.
So this
I guess
is
this is like Geiser or something.
sorry.
I guess this is due to Thomas Geiser or something like this. I mean, this is
No. This is the theorem of myself and Srinivas.
sorry, not for surfaces, for higher dimensional.
No, in higher dimension. Yes.
Yeah. Thank you.
Yeah, in higher dimension. One shown by Thomas Geiser is totally different. That is not this Chow group. That's a kind of homological Chow group, not this Chow group.
Okay.
That's a Fulton Chow group.
I see. Okay.
It's not this Chow group.
Not a living.
That's the difference.
Okay.
Yeah.
Thank you.
Right. And so so you know that this is uniquely divisible. Now I claim that this quotient is also uniquely divisible. Well, because because W and WR are affine surfaces, and this is a classical theorem already in the book of Bass, that SK1 does not see, SK1 is nil invariant for these curves. So I can assume that both W bar and W are reduced. But then it's basically it's not hard to see that SK1 is uniquely divisible. And this is one reference for this is a paper of Barbieri, Viale, Pedrini, and Weibel. One of the results lemmas, they prove that in that case, SK1 is uniquely divisible. So we know that, So we know that this quotient is uniquely divisible. Then if you do some diagram chase, all you need to prove to finish the proof that this Chow group of X is uniquely divisible is that the H1 X bar K2 is divisible, not uniquely divisible, only divisible. So the whole problem is left is to prove is this group is divisible, and that is the heart of the proof actually. So you see that this is the hardest part, which I will not give the proof, that why this is divisible. Okay. So this is the main step you have to prove, and this requires a lot of work. Okay, so I skip the proof because this is very difficult to say here.
Sorry, is H1 X bar K2 uniquely divisible or just divisible?
No, I don't think it is uniquely divisible. It's just divisible.
Okay, so it's divisible. Okay.
And that's enough for us.
Okay.
Yeah. So now let's go to the higher dimension case. So you will see like what happens here. So you will see. So suppose D is at least 3 now, and let alpha be a 0 cycle, so that n times alpha is rationally equivalent to 0 for some positive integer n. We need to show that alpha is rationally equivalent to 0, right? So let C1, F1, blah, 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 CR, FR be a collection of curves and rational functions on them, so that n alpha is the sum of these divisors of F. And take C equal to union of Ci. Now, what's the idea? So how do you reduce dimension? So idea now is you can choose a complete intersection surface Y inside X, which contains C. Suppose you can do that and assume that Y is regular along the support of alpha, and Ci are Cartier curves on Y. Then it follows that alpha is a torsion cycle on Y, but Y is a surface. So we already know that then alpha must be rationally equivalent to 0 on Y. And then by pushing forward from Y to X, we just prove that alpha has to be rationally equivalent to 0 on X. So we are done. But I am cheating here. The problem is that you cannot do this. That you cannot say that if I have this curve C, then I can find a nice surface which satisfies all these conditions inside X. You cannot do this in general. In a specific problem you may, but in general you cannot claim that. So the problem, however, is that we cannot ensure all these conditions together. So we have to do something else. So what do we do is the following. So to solve the problem, we blow up the bad points of C, such that now C becomes nice enough. So in particular, every component of C becomes regular along the regular locus of X, and their component intersect transversely. Suppose we can do that. By blowing up, you can do that along this regular locus. But then now we can find a surface Y which contains C and on which the support of alpha consists of regular point of Y. You can do that. But the problem now is that the new problem we face is now Y is no more affine, right? Because you have done the blow up of X. So if you take a affine variety and blow up enough number of times, then you lose the affineness. It becomes a very bad scheme. So although you can find a Y there which contains your C, but Y is no more affine. So I cannot apply my affine Roitman torsion theorem for surface. So to take care of this, actually what we do is the following, which I did not tell you. So let me go back to 0 dimension case here. Actually, what we prove in the paper is that if you have a quasi-projective surface, a very general quasi-projective surface, almost very general, not arbitrary, but good enough for our paper, almost general, then, and it's not projective, then the Chow group is torsion free. It's a strong statement. It's not only true for a affine surface, but I claim it is true for almost all non-projective quasi-projective surface. So then this proof does not work, this exact sequence. So I have to do some other things. So that's why I cheated you here. So when I give you the proof, I assume that my X is a affine surface, but that's not enough. We have to prove something else. So that is what I am saying here. So you have, then if you prove for such Y, then Y is, then the alpha is rationally equivalent to 0 on Y, and then again you can push forward to X. So that's the whole proof. So you see that eventually you have to do some lot of work there. It's not just like very simple like this. Yeah, but the idea is that. So you have to prove the Roitman torsion for not only a affine surface, but more general quasi-projective surface. So that proves the theorem A. So now let me go in 3 minutes I have. So let me just give you a current research. So I now briefly discuss some of my ongoing projects related to the problems we discussed. So throughout our discussion, remember that we assumed K is algebraically closed, but now we relax this condition. So then we cannot expect the Euler class group to coincide with the Chow group. If X is affine and smooth, we can replace the Chow group by the Chow bit group. We can do a similar thing for affine, but not necessarily a smooth scheme. So what I do is that I can define a notion of what is called Levin-Weibull Chow bit group, which I write at CS0 tilde LWX for any, in fact, we can define for any variety X. Now, assuming X equal to A is affine, you can actually construct the following diagram. Here you have the Euler class group. This is the weak Euler class group. And this is your Levin-Weibull Chow bit group. This is your Levin-Weibull Chow group. And you have a commutative diagram. And what we expect is that we expect the vertical arrows to be isomorphisms. Namely, that Euler class group should be Chow bit group, and weak Euler class group should be Levin-Weibull Chow group. So this is the problem I am currently interested in and I'm studying. And there are like similar problems on this topic. In fact, some of these problems I am currently working out jointly with Eldon Elmanto. Like what happens to, for example, these kind of maps. Namely, you take the Chow bit group and take Chow group. Can you say something about in particular what the kernel is? So these are the problems actually I am working with Eldon. So note that if A is smooth and K is infinite perfect of characteristic not equal to 2, then there is a recent result of Ashok and Fazal which says that beta and alpha, namely the vertical maps, are indeed isomorphisms. And this was the conjecture of Bhattacharya and Sridharan, that weak Euler class group should be isomorphic to Levin-Weibull Chow group without any condition on the field, actually. So this is still open. So we are hoping that we can prove something here. So that's the kind of current state of affairs, which yeah. So that's the basically the end of my talk actually. Thank you very much.
Thank you, Amalendu. Let's give him another round of applause. Any questions for the speaker? I have one question.
Yeah.
So when you say very general quasi-projective surfaces, you mean something like projective over an affine? Is that the kind of thing that's true? Or is that too
yeah, I mean, I did not prove in this generality that if you take a projective, if you take a affine surface and take anything projective over this, but the proof essentially, because I did not need it, but the proof which I was using, my proof essentially says that it might be, what you said might be actually true. That I expect that it might be true that if you take a fine surface and take something projective over this, then the Chow group should be torsion free. Yes. Right. In particular, if you take this is definitely true that if you take a fine surface and take its resolution of singularities,
right,
then its Chow group is torsion free.
Right. Okay. Any other questions? Okay, if not,
if I could ask if I could just have a quick question. Sorry, I think maybe could you say again, sort of like how generally is the Roy? I mean, is this type of I guess this. I mean, what would be sort of the most general form of like this Roitman's torsion theorem?
Actually, yeah. I mean, I have no. I would like to actually, instead of predicting anything, I would like to ask this question that I think the most general thing would be that you take, as Eldon already said, that take a affine variety over algebraically closed field, any affine variety, and take anything which is, let's say, projective over this. Yeah, or let's say, in particular, you can take anything which is birational to this, and which maps there is a proper map from X to this affine variety. Then I would like to ask that is the Chow group of zero cycle torsion free, and this is not known at all. Even in the smooth case, this is not known.
Sorry, this is affine of dimension at least 2 or something.
Yes.
This is affine, the affine basis of dimension at least 2.
No, it's any dimension.
But what if you have something over a point? I am asking
this question for any dimension. Yes.
Sorry, but what if you have like a projective variety over? I mean, just over a point.
No, sorry. It is the variety has dimension at least 2.
Okay.
The fine variety has dimension at least 2, not even dimension 1. Yeah, even already in dimension 1, this is false. So if you have dimension at least 2, then I don't know. Then this is my question. So the proof which I was writing in my paper, it looked like if dimension is 2, then this should be true. But I don't know how to prove this in higher dimension. Maybe the trick of Bertini might work there also, I guess. But I did not pursue this. But that would be the very general Roitman torsion theorem.
Amalendu, do you have some sort of an analog of that Maia-Vitor sequence for Chow groups that we hold for Chow-Vid groups?
Chow-Vid group, you mean the Roitman torsion for Chow-Vid group?
The one where you had the H1 XK2 going to the SK1 quotient going to Chow 0, going to Chow 0, going to Chow 0.
Yes.
If
Oh,
you-
for the, you mean for whether something like that for the Chow group you're asking?
Yeah,
Okay, let me go back to that. Oh, this
Here.
one?
Yeah.
I believe so. I believe yes, because so for that I have to give you a definition of this. And then essentially this here you will have some kind of authentic width group here of curves. And
Some kind of a what group?
Huh?
I didn't hear you. Some kind of a what group?
Some kind of authentic width group you will have to take.
Mm-hmm.
And then I expect, I have not proven it, but I do expect this to be true, because the way I define this is basically my generators are the Milnor-Witt groups of the rational regular closed points, and generator comes from the K1 Milnor-Witt group of the curves, Cartier curves. And then if you try to prove this, try to see the proof of this, I guess there should be something, but I still don't have a concrete statement, but I believe this should be true. Because this basically this is proven by just going to K theory, and as you said, using some bare varieties. And I believe that that is what I was asking Ellen few days ago, that if you have normalization map at least, then do you have mere varieties for authentic bit groups? And if you answer is yes, then you can have this exact sequence.
Great, thank you.
Yeah.
Okay, let's thank Amalendu again for a nice talk. Okay. All right. Thank you, Amalendu, for
thank you, Ellen. Thanks. Bye.
The weird
Yeah. Thank you for the talk.
Thank you for the talk. Okay, well, he exited. All right.
Okay.
So shall I pause, stop recording? Yeah, all right.